So in this lecture, our goal is to introducing the continue our discussions on the level set plasticity, but more importantly, I would like to finish the lecture quick, and then you guys probably already see the Jupyter notebooks, and then you may see that some key programming, unlike the first time, are actually missing. So so that would be interesting. So we'd like to help you fill out those missing pieces step by step. Okay, so just bear with me. I would talk about what we talked about last time, but with more implementation details. Okay, so last time we just go through the theory, the big picture, but here we were going to simplify our goal to just try to do something very simple, like a J2 plasticity. But the methodology we talk about in principle should work for any pressure insensitive material. Okay, so so hopefully we can finish the first hour with the presentations, and then have the last hour focus on the tutorial. Okay. So we are actually almost finishing the traditional discussions on the neural network training, and then in February we'll switch gear to extend the current model with the geometrical learning. So what you learn, you can consider it as a geometric learning, or you can consider it as just learning a function in a vector space, not necessarily using any understanding on the topology or metaphor. But we're going to changing that. So and I'm going to extend the deadline for the lab number 2 to a later time, and I think that I have updated this in Canvas. Okay, so this is the last lecture. We actually covered the first 3 items very briefly, and then we talk about we haven't get a chance to talk about the in-class numerical experiment, so this time I'm going to go through that. And then in this tutorial, I will focus on something simpler. Instead of trying to do a micromorphic, micropolar, and a subtropic plasticity, I'm going to do something that are completely redundant of using neural network to do it. You can just write a classic model, but then the idea is for you to go through the workflow of how to build a model that actually have elastic and plastic module. Okay. So, and then for simplicity, I would already assume that I have a linear model, so I won't change the elastic model. So I'm just focused on the plasticity model, and I'm going to just focus on the perfect plasticity. So perfect plasticity, if you haven't taken a plasticity course, which that just simply meaning that the yielding, the combination of yielding stress is not going to change. Okay, so that would actually simplify the whole case, because last time you see those balls that are evolving from a circle to an ellipsoidal to a different shape, that is actually because of the hardening and softening, and hence the revolution of the U surface. So we're going to take that out, and then we're just going to focus on the algorithm design, and that hopefully I can go for the tutorial. Okay, so the tutorial, how many of you have taken a look in the second lab? So you see the color ball, okay, in the piping. This is actually the von Mises U surface implicit functions. And what you need to do is actually to complete the implementations of it, or maybe if you like, introduce some hardening, softening. That would be actually interesting. But this is actually what we're trying to do. Okay, so J2 plasticity model, you can also, the reason to do that is that you can also verify it. Okay, easily. I checked it this morning with ChatGPT. It's still not able to do it yet. By the way, it did get the common white. I mean, I'm quite impressed. It say that check U surface and make the correction. It's just that the ChatGPT is not really distinguish the tensor from a. Anyway, so we would assume we already have the elasticity, and then we are giving some yielding point. And then I'm going to go over the level set theory in details on how to create to constitute the supervised learning problem. Okay, so how to create a label to complete the supervised learning, which is not super machine learning easy, but more on handling the geometry. Okay, so we're going to, hopefully at the end of this class, we can actually answer that one questions. Hopefully you can build a perfect plasticity model. And with that, you can actually later on extend it to something more evolved. Okay. Okay, as I mentioned before, plasticity model, or more accurately, the elastoplasticity model have the following criteria. You need underlying elasticity model. Okay, this is actually when you're using it when you need the model to be unload. Okay. You actually need to have an underlying elasticity model to actually you're going to continue using it to predict the stress, and I'm going to have some derivations for those of you who may not have taken a plasticity class. Okay, and then we also still need a plastic flow. Okay, we need to know what kind of plastic that formation is generating, but because it's perfect plasticity, we don't need the hardening law, which is actually related to the Hamilton-Jacobi or the Ericsson problem that we actually need to solve. So that should sufficiently simplify the model, and we're going to write an algorithm that given the stress and strain and historical variable in the previous day and then the current stress. So this is actually all given. Okay, this part we're going to update the stress and the history dependent variable. Okay, so some of them we already talked about it in the last class. So here I just want to quickly overview the J2 plasticity. How many of you think that it would be helpful to review the J2 plasticity, or how many of you think it's redundant? Okay, I'll give a very quick review. Okay, so we have a stress. Okay, and the stress, let me using this. Okay, and the stress is that you can consider the stress as a matrix, or actually as a tensor. We would actually use two index to indicate that it has two directions. A stress can be decomposed into the volumetric part and the rhetoric part. Okay, so the volumetric part is actually simply equals to the pressure times the identity tensor, and pressure is simply equals to 1/3 of the chase of the stress tensor. And what it means is that you just add the diagonal term together. Okay. Now, what is a rhetoric stress? A rhetoric stress is actually simply the let me put the ij there. Okay, in the index form, I write something like that. So this is actually the delta matrix. So and delta II is actually equals to delta II is actually corresponding to equals to 1. For example, delta 1 equals to 1, delta 2 equals to 1, delta 3 equals to 1, and the delta II, strictly speaking, is actually equals to delta 1 plus delta 2 plus delta 3, which is actually equals to 3. Okay, so and that one is actually equal to the chase of the identity. Okay, so let me see where I can try to add up. Okay, maybe that will be better. Okay, so with that, what actually is important is that in the J2 plasticity, if we remember what we talked about last time, we have sigma 1, sigma 2, sigma 3, and there's a hydrostatic axis where sigma 2 equal to sigma 2, sigma 1 equal to sigma 2 equal to sigma 3, and the von Mises parasiticity model is simply a cylindrical object in the principal stress space where the radius along the line of the hydrostatic axis is actually it doesn't change. Okay, so it remains constant. So what we actually should do is that we should actually taking out the dependence of P and then simply focus on the directoric stress. Okay, so we can write the directoric stress as the total stress minus the Pi. Now this is actually in the tensor notation, so I don't write out the index, and then P would be equal to 1/3 of the stress. That's what we talk about. Now what we actually need to obtain is actually writing the U surface as a function of S. Okay, and S is actually simply equal to the directoric stress sigma y than Pi. Now, because the stress is actually taking out the chase part, it will be independent of the Passer behavior, but the directoric stress is actually still a tensor, so it's actually not so convenient to use. So what we typically did is that we would actually have using the S double dot stress as the norm of the stress, the directoric stress, and this is actually used to write the U functions. So let me give a summary. The U function initially is actually depends on sigma ij, okay, for perfect parasiticity. Now I'm going to simplify it. Assuming isotropic behavior, we're going to simplify it as sigma 1, sigma 2, and sigma 3. Now I'm going to actually only represent it as a functions of the tensor, the scalar product of the directoric stress. Now this actually create a one parameter problem. So that would actually make the whole thing very simple. Now, in the case that, so in the piping, what it actually lead to is actually simply a circle, because the only thing you control S is actually simply the radius of the stress. However, the drawback of this approach is that if your U function is actually not a circle, one parameter is not sufficient. So this approach is only useful for the J2 parasiticity. Now, in the general case, we have the following machinery. We need, in the 3D classical theory, we need the following ingredient for the parasiticity. Okay, so for the pressure insensitive material, we actually need to partition the strain into the elastic part and the plastic part. Okay, the plastic part is actually the one that doesn't contribute to the stress. If I take the time derivative of it, I will get the change of the strain equals to the change of the elastic strain plus the change of the plastic strain. Okay, so far so good. And the important thing that we want to is that the stress update. Stress is actually only given by in the linear elasticity case is only given by so the stiffness tensor times the change of the stress is only equal to the stiffness tensor times the change of the total strain minus the change of the plastic strain, which means that it only depends on the elastic strain. Okay, so double dot here have a very specific meaning. If you're actually familiar with the tensor calculus, it means CIJKL E times epsilon dot E KL, and then KL and KL dummy index. This is actually extensions of the vector dot product in And in the undergraduate finite element course, that would actually lead to a C matrix that are 6 by 6, and that would lead to a vector that are 6 by 1. Okay, and then you would actually this product that actually is supposed to lead to the stress change would be actually equals to the would be actually carried out in a dot product calculations. Okay, I won't go over that in details, but then for the elasticity theory to work, we basically need 3 ingredients. We actually need to find the partitions between the elastic part and plastic part in each time step. So we need to know, given this total step, how much of it is elastic, how much of it is plastic. We don't know. Okay, when we actually make a numerical calculation, we just assume everything is elastic. So we first assume epsilon dot p is actually 0, and then we actually find out how wrong it is, and then we actually create the corrections. Okay, that corrections is actually using the geometrical problem that we talk about. In order to make the corrections, what we actually need is actually to use efforts. So let me compute that. So we need the following ingredient. We need the partitions of the elastic plastic strain and elastic portions of the strain and the plastic portion of the strain. Combine them, I get the total strain. So this is actually called strain partitions. And we need another ingredient, which is actually the change of the stress is only equals to the elastic part of the strain, but not the plastic part. Okay. And here I'm assuming linear elasticity. If the elasticity is non-linear, this CET will become the tangent. So let me explain the following. If you have a linear elasticity, okay, the slope of it is actually not changing in the 1D analog. So your tangent is actually just the slope. Okay, in the nonlinear elasticity, the major difference is that your strain is actually nonlinear, and hence it makes no sense to map it from here to here, because the slope of this, and then the slope, and then the tangential slope, this is actually not identical. So for the nonlinear problem, what you actually need is that for the elasticity problem, you actually don't need the waveform. You can directly compute the stress from the previous strain. You don't need to do it incrementally. But for the nonlinear problem, you need to know where you are, and then you need to obtain the tangent that are actually only good in these current positions, and then you obtain the linearized solutions. Okay, so here I'm just assuming a linear elasticity to simplify the problem. And then the third ingredient I need to use is simply to ensure that the yield stress in the case of perfect plasticity is actually, if I evaluating it, is either equal to 0 or smaller than 0. It cannot be bigger than 0. And then the fourth ingredient is that I need the plastic strain to be equal to something called a plastic multiplier times the stress gradient. Okay, the stress gradient itself, if I write it in index form, is actually a second order tensor, and then epsilon dot p is a second order tensor, and lambda dot is actually the magnitude. Okay, so that split actually gives us two things. This part tells us what kind of plastic strain I have, plastic deformations. Okay, when I say what kind, it means that is the plastic strain volumetric? Is it compactions? Is it shear? If it's shear, is it in this direction and that directions? But it doesn't tell you the magnitude. And the elastoplastic model is to actually, the trick is to given this magnitude and then find the lambda dot, because to find the scalar lambda dot is much easier than finding the flow directions and the dot. So And this one, we simply assuming that the type of the plastic deformation that you generate are actually the same as the mode of the stress gradient. Okay, so you have a U surface that looks like this. If I take the gradient, so let me give you an example. Okay, I'm just imagine something. If I have the directoric stress, and then I have a pressure. Okay, so pressure actually is related to the stress that are applied homogeneously, usually associated with size, and the directorial stress are actually corresponding to shape for the isotropic material. If you change the shape, you need to change your directorial stress for isotropic material. If you want to change the size, you need to apply the mean pressure. Okay, roughly, if it's isotropic. If it's isotropic, there is no coupling between the directoric mode and the volumetric mode. So what it means, the stress gradient have the following physical meaning. In a von Mises stress, the U surface in this directoric volumetric space is actually independent of P. So what it means is that I will just have that straight line. Okay, so it's not sensitive to P, meaning that if I change the P, I will get the same radius, right? Okay, for that straight line, I would actually shoot up. This would be my normal vector, right? Okay, what is the physical meaning of that normal vector is that I'm going to actually create more plastic strength only on changing the shape. Okay, so this is actually a purely directoric deformations, or enlarged deformation, we call it isochoric deformation. What it means is that there is no plastic portion related to change of the volume. Okay. Now consider another case. If I want to write pressure sensitive material, instead I'll have something like this. Okay, so what happened here is that now my normal vector is actually pointing to these directions. Okay, now if you look at the details of these directions, it has two components. One is actually these directions, okay, you see that? Another portions is actually these directions. Okay, so what it means is that if I create plastic strength for a given part of the change on the P, okay, I actually need to have a portions of it changing the S. Okay, so what it means is that if you convert it into a kinematic view, is that if I actually have a plastic strength on the shear, if I change the size, if I change the shape of the material, that permanent, I'm also going to change the size permanently. Okay, so this is actually, this angle is called friction angle, and then the more friction angle you have, the more portions that you will see on actually governing the change of the volume and the directorial mode. Okay, so the same idea can be extended to piping. Okay, in the piping, I have XS sigma 1, sigma 2, sigma 3. I have some arbitrary shape, maybe like a Tresca one. Okay, what I mean is that what you actually need is actually the plastic flow is actually just this. Okay, but then for different locations, you have different plastic flow, right? And actually here, you actually don't have this one. You have both of them actually being valid, right? It's bifurcated. So what it means is that you actually have a specific type of the plastic strength that are actually developed according to the flow directions. So that's why it's called flow directions. It's not really a directions because it's not a vector, okay? It could be, it's actually corresponding to a second order tensor, but it's corresponding to the mode, okay? So why do I need to explain that is that if you actually write a plasticity model, it's actually not like the classical supervised learning. I just mount those learn functions on the point where f equal to 0, that's good enough. I also need to control the orientations. If you don't control the orientations correctly, you could have the following problem. Let's say we have a Tresca U surface and I just analyze a portion of it. Okay, what you actually obtain from the physical data is just some point. Okay, so as we see before, you can link it with this point, which is actually good, but you can actually equally reduce the second order tensor if you actually have these oscillations. Okay, it will actually, if you're actually sampling it with the dot, you won't actually tell the difference. Okay, this is actually why you need the higher order term. Long story short, we actually have this ingredient, and in this case, you actually need to actually have a spectral decompositions of it. I won't have time to talk about all the details here, but what we actually need to do the surgery is only this part. So in your first lab, you create an elasticity model. In this lab, I'm just going to create that learn functions. Okay, it's a scalar functions, and then you take the stress as an input and only output a scalar. And then that scalar is actually called indicator functions. It actually tells you where you are. Okay, so there's only, you actually give you a partitions of the set of the data. Like what we mentioned before, inside the U surface is actually elastic. Okay, on the boundary is actually yielding. And then outside is immiscible. Basically, immiscible window is the wrong answer. You need to correct it. Okay, so no admissible answers is the right outside. If you use an explicit scheme to update it, you may find that your stress is actually outside, and stress speaking is actually not correct. But you can actually assume it. Sometimes explicit scheme is also used, but we won't talk about that. So, and as a result, we need to change that yield functions, and we also need to control the gradient. One problem is the ring, and we talked about it before. Let's say I have a U surface. I already have the implicit yield functions, and then what you need to do to change the entire U surface is actually very simple. I just have a point cloud everywhere. I just write these functions, okay, and then I create a point. I create a loss of point here. Okay, and then I evaluate f, then I would actually get the label, right? So f is actually the output, and then f is actually the output, and sigma 1, sigma 2, sigma 3 is the input, and then that should be it, okay, if you know the functions. However, in a physical experiment, you actually only detect when does it yield, and you call it the yield point, right? So you don't have function inside and outside. So if you're only training the yield functions, if you only have the supervised learning on f equal to 0, your resultant learn function will be very unstable. Okay, and this is actually not really usable, because for the mechanics problem, a lot of time you need something that is smooth. Usually we assume too much smoothness, or actually we assume a specific fixed hypothesis like linear elasticity. You need to. Okay, so we actually need that. And so the first step we need to do is do a data preparation. So let me go over that else. So the data we actually need to perform or obtain can be obtained from physical simulations, or it can obtain from direct numerical simulations of MD simulations, or if you have a micro-CT image, you can also deform your micro-CT image, and then and if you know the constituent material behavior, you can observe the yielding. So you can start here that is actually stress-free and low different combination of stress. Okay, so that means that you apply the different stress on the specimen, different combination of sigma 1, 2, and 3. So here we do a trick. We actually start with the triangle just to save some time. But what you actually would recover is actually a point cloud where f equal to 0. Okay, so in this point cloud, f equal to 0. Okay, we know that f equal to 0 here, but we don't have any inside or outside informations. So if you actually directly learn it, it will not be very stable. Okay, and what you may actually want to actually collect as a result is the two type of informations. The information type is actually what stress does the material yield. Okay, so I can loading it for example, I can actually loading it in a uniaxial loading, and I wait until the material yield, and then I measure the stress, and then I calculate the stress eigenvector, and then I will get one single point. Okay, and at that single point, I need to collect another informations. which is what kind of particle strength I have. Okay, so this can be easily done because if you have an elasticity model, the slope in the or in an analog in 1D, the slope will be actually a straight line, right? If you have an elastoplastic behavior, it will be following the elastic string, and then it would actually have a particle branching out. So this part is actually the U point, and from that, from comparing the discrepancy, you can actually, because you know the stress, and the stress change is actually equals to the elastic strength double dot the total change minus the particle change. Because you know the stress change and you know the elasticity and you know the total, you can back calculate the particle strength. Okay, and then normalizing that particle strength, you can actually get the stress gradient, because the stress gradient is equal to the lambda dot of the stress gradient is actually equals to the epsilon dot p, right? And here you don't really care about the magnitude of lambda, you just care about the ratio between of the U functions. On the piping, or actually in the principal straits, you have an advantage because in general, I have to consider this second order tensor, right? Okay, that gives you the flow directions. But in the principal stress, this becomes just a vector because for isotropic model, there is no, the U surface is actually not depends on the orientations of the eigenvector and only depends on the eigenvalues. So this becomes just a set of a vector in the R3 space. Okay, I only care about a vector. So this would be the vector that we actually need to collect, and this is actually collect from solving that problem. Okay, if I give more details, that would be epsilon dot equal to CE double dot epsilon dot minus epsilon dot P. And then what I actually need to do is actually obtain the inverse of it, and then I will have the C dot equal to the C total minus epsilon dot P. And after that, I would actually moving this, so I have the epsilon dot P, epsilon dot minus epsilon E minus 1, epsilon dot. Now, so if I actually know the orientation of this, yeah, I think I read it correctly. Okay, if I know the orientations of this, I can actually compute the, I can actually obtain the direction. So this one is known, and this one is known from experiment. Okay, and then CE is actually invertible for linear elasticity. It will be very dense, but since it's linear, you don't actually need to update it, so it won't cost too much to store the inverse. Okay, with that, then how do I actually get the flow directions? Okay, you do one thing is that remember that this is actually equal to epsilon dot P. So I would actually have this equal to 1 divided by lambda total epsilon minus CE minus 1 double dot epsilon. Okay, and because I only care about the ratio of the gradient, I don't really care about the magnitude. I can actually just obtain the, I can actually just normalize this term, and I will get the stress gradient. Okay, you see what I mean? So for a given point. So what you actually get, if you actually think about it, now I would, in the piping, if you think about the individual data, it's like I'm giving you a point, but I'm also fixing the orientation. I'm saying that the tangent is there and the normal direction is there. Okay, I'm giving you the type of information that look like this. Okay, does that make sense to you? Okay, I'm saying that in order to link them together, I have the tangential direction has to be here. It cannot be other angle, and the normal direction has to be here. So it gives you more control to link them together. Okay, versus if I do the classical L2 norm, I will simply get a bunch of points. and then there's no orientation information. So I can actually link it in a more different way to actually reduce the L2 norm in the same manner. Okay, you see what I'm saying? As I mentioned before, if you only have this data obtained, now then what actually happened is that experiment, you cannot learn a very stable yield functions. Here I'm talking about the property of the yield function, not on predicting the f equal to 0, but how robust your yield function is. So I need to actually introduce a data admin stuff. So remember, you are training the yield functions that actually mapping the a stress, principal stress onto a scalar, okay? And this is actually, R3 is actually basically any stress combinations, not only on the boundary. So basically need a point cloud. What you actually have is this, plus the orientations only at f equal to 0. What you need is actually the data that are everywhere. You need a point cloud that populate everywhere in order to constitute the learning function to actually control the learning function. So the thing is that you're already giving this point cloud. How do I get the rest of the point cloud that are actually meaningful? Okay, does that make sense? Okay, so so what I'm saying is that if you actually want to do a supervised learning, for example, you want to change a scalar R2, you definitely need to have the supporting point everywhere. That would actually make the training easier. Or you can add more constraint, okay? But you can find that in general, if you have a supporting point, that would make the supervised learning much easier than you actually have the constraint, okay? Simply because when you actually training the point set, that less likely to encounter a lot of non-convex local minimizer. Okay, so the way it need to do in this, we have a lot of advanced things to do, including using MATLAB to do the sign distance transform, which I'm sure I can assure you that you actually need to type the MATLAB level set transform, which is not easy, I guess. But here, because we can assume something to make the problem even easier. We can assuming that the yield surface is convex, and that convexity can actually make the problem much easier. We can use something called particle marker formulations. The idea is actually very simple. Okay, I want to populate the entire R3 space. Okay, I don't want to just have the point here. I want to have some point here. I want to have some point here. But the fact is that I don't actually need to know the values inside and outside. I only need to know the value f equal to 0 to be correct. I need the gradient to be correct. But inside and outside all the other value, I just need to have the right sign. The sign has to be correct, right? Because the yield function is just to check whether f equal to 0. Okay, you see what I mean? Whether f is greater than 0. Okay, so I only care about the sign. So I can actually put whatever function I want if the f equal to 0 is right, and then the gradient of f equal to 0 is right. But I can actually pick some simple pattern to make the learn function a little bit easier to learn. And one of it is actually the sign distance functions. Okay, so we can easily extending the values here by solving a problem called velocity extensions. So if you take a level set class, you probably you probably see that functions. Okay, so f is actually a scalar, and it's called a speed functions. So speed function tell you if you're giving implicit functions, how does the interface evolve, and then it could be anything from a scalar, or it can be related to the curvature. If it's related to curvature, we call it curvature flow. But here it could be just I would just assign a scalar. Okay, because I don't care about the to evolve a complex pattern to actually simulate the solidifications of metal or ice. I just want to extend the values, and then I will use the n as the stress gradient. Okay, and then I'm going to solve these functions. So if I'm solving it in finite difference, it's actually not that interesting. If I assign f as a constant, I simply have n. If let's say f is actually simply 1, then what I would have is that I simply extending the point equals to the normal vector. Okay, so what does that mean? The delta t is actually not an actual physical time, it's just a fixed values corresponding to the speed. So you can actually just take it out here. So what I'm actually trying to do here is that if I have a point here, I'm just using that normal vector to, and giving a constant speed. So the speed control how far I travel to locate another point here. And to locate another point here, and another point here, and another point here at a given time. And if I have a point here, I can actually using the normal to keep extending the point. Okay, if you're pointing it outward, eventually you can actually get a lot of point, and then accept this f equal to 0, you can simply using the distance here as the value of this point, right? You see what I mean? So f would be actually simply equals to the distance here. Okay, and then I will assign this point equals to the distance here. So f another point is actually equals to d2, and so on and so forth. So I can actually populate the entire point cloud in the normal directions. Okay, outside. Okay, so outside is easy. Okay, so does that make sense to you? Okay. Now then I will have a point, and then that point would all give me f greater than 0, and it won't be used, but it will be actually populated as a shape. Now the important thing is that this only works for convexity problem. You can already see the problem if you have something like this. So what will happen? Okay, so it will collide with each other if you actually have a constant speed. Eventually you will have some pattern that are overlap with each other, and then it won't work. So it only works for convexity and then pointing outward. If you're pointing inward, it would also work, but you have to stop before the thing shrink to a point. Okay, but so far so good. Okay, so you would, in this case, in a more, so level set, lots of the level set technique is apply on finite volume, not on point cloud. So if you actually use it, you can also apply it in a more classical finite volume thing, but you need to do the interpretation and apply the grid in the background, and you actually need to interpret what is the function value in those points. And here I'm just, I just provide a easier approach, just use the particle marker approach, but the particle marker have this own limitations, and they only work for convex. But as you may see, we won't deal with the non-convex U function that often, so usually that's fine. Because if you have a non-convex function, it may violate the thermodynamic rules anyway. Okay. Okay, so so this is just to show you, to pointing it outward, this is actually a curvature flow. The speed function is actually not constant, but have a different growth rate in different point, and you can see that it have the overlap. Okay. Actually, in our case, it may not be a big deal because, but you may get a wrong side distance functions. But if you only care about the sign, it may actually be okay. You just have a more weird pattern. But this weird pattern, you're not using it anyway. Okay, so, but just aware of that. So here, I will recommend that if you want to train the neural network. The thing is that if you train it in the neural network, you just need a point cloud. It doesn't need to be regular. Okay, because your point is considered as a set. So that may be easy to populate the data. This is just some example of the U function that you can obtain from that. By the way, I haven't applied any neural network. I haven't trained any neural network here. I'm just providing the data that are making it easy to train. As you can see, the speed function is simply 1. And in this case, you also don't have to solve the level set problem. You can just using a marker to get the sign distance function. Just be aware that if you keep growing -1, this string shrink into a point and then they overlap. Does that make sense? Because the speed function, if you don't reducing it, it will keep shrinking, and then it won't detect the. The Lagrangian approach doesn't necessarily allow you to detect the overlapping. Okay. Okay, that's it. Is that clear? So this is, I need to explain it in details because you need to think about whether you want to using this to prepare the data. So this is the data augmentations process, particularly for functions. And now we need, to formulate the supervised learning problem. To formulate the supervised learning problem, in the elasticity part, you're given a string tensor, and you write the string tensor as a functions of the string, and you simply need to change the scalar functions. And then you take the derivative, you get the stress, you take the second derivative, you get the string. You can use something called Sobolev training to achieving that. For the U functions, what you did, actually the nice thing about this is that they actually, the training is almost identical. Okay, you just simply need to build a new network and you change the meaning of your input and output, and that's it. Okay, once you prepare the data, it's actually, I guess the nice thing is simplicity. You can actually reuse your elasticity learning hyperparameter to change your yield functions. And to be honest, your yield function may even have a simpler thing than the. You may actually find it change the yield function even easier than the elasticity, simply because for the sign distance function, you use a sign distance function, right? So your gradient is actually equal to 1. So what is the curvature? Okay, so you can actually have an easier time to deal with it. Now, in general, in the yield functions is not just the functions of the yield surface. The yield function is not just the function of the stress, but also the function of the internal variable, because the yield functions have to be evolved with some historic parameter. For perfectly positivity, I will kill off this part so that you actually simply need to compute f as a function of the stress. That would actually make it identical in terms of the dimension size with the elasticity model. Okay, so if the material is isotropic, your input would be just sigma 1, sigma 2, sigma 3. And if the material is also yielding isotropically, your input will be sigma 1, sigma 2, sigma 3. And then you come up with functions that are actually epsilon 1, epsilon 2, epsilon 3 here. And here you would also get f equals to sigma 1, sigma 2, sigma 3. Okay, the difference is that the point cloud that is distributed is actually a little bit different. So here, when you train the material, only f equal to 0 is actually the real data. All the other data are the one that you add just for controlling the geometry. Okay, and you can actually also apply different way for the two U surface to mount the U surface so that it doesn't move, and for all the supporting points that are less important, because you don't really care about the values of your supporting point. You're just using it as a hint to control the shape of the surface. Okay, so there are different options and you can actually play around with it, and that is actually one of the interesting part. For J2 plasticity, you can actually train just with the U surface point cloud. Okay, you just you remember that after you're training that, for given sigma 1, sigma 2, sigma 3, you know whether f is equal to 0. And now, but with the data augmentations, you also have the f outside the U surface, you have the values, and f inside the U surface, you have the value. So you have the value everywhere. Well, not everywhere, but on the point cloud that you actually select to actually add more control point, right? Okay, so and you can put it like that, or you can actually add a different way in that wave function so that your actual f equal to 0 point cloud are viewed more importantly. Okay, and then you can add less weight for all the other supporting points. Now, for the H1 norm, in the principal stress space, what you actually need is to add this term here. This is an additional term, and this is actually not coming from directly from the yield function, but like what I said is coming from the measurement, coming from the incremental plastic strain. Okay, at the initial yielding, right? Okay, you remember that derivations? And then you actually control that to be aligned with each other. There are also other tricks, because we knowing that in the piping, I simply have an angle. Okay, you see that in the piping, I basically can describe the orientation with just this angle, counting from sigma 1, right? Okay, you can also using that angle to actually control the flow directions. One drawback of that is that one drawback of this using the angle approach is that if you actually have an angle like this and then you have another angle like this, it will look very different, but they could be just 1 degree apart. Okay, so if you're already matching it pretty well, that's fine. But if you actually have a finite rotations, that can lead to some funny, or actually if you're close to the 0 degree, then it could cause some problem. Okay, another way to represent the orientations is to use the rotation tensor. Again, if you normalize that sigma 1, sigma 3, sigma 2 directions, okay, if you're normalizing that, you can actually get phi orthogonal tensor, phi orthogonal vector, and then you sum it, you put it together, you can get the rotations. You can actually simply check whether that rotations that you obtain from the neural network and the rotation you obtain from the parsec flow are actually equal to the identity. Okay, so because if R1 equals to R2, then what it means is that R1 transpose is actually equals to R1 minus 1 equals to R2 minus 1. Okay, so, and if this is the case, then R1 R2T is simply equals to R1 R2 minus 1. Okay, so sorry, minus 1. So it can cancel each other. It will go back to the identity. There are other ways to do it, but I think that in general, you shouldn't see that much difference because, for example, for J2 plasticity, why is that? Because you just have a circle, and then it doesn't really have that. If your shape is very simple, your normal vector change gradually. Okay, if you actually represent it as an angle, it simply just grow in a constant manner, right? Okay, versus if you have this shape, okay, and if you look at that angle, you actually have some problem here because you have this stress gradient, they are both valid. Okay, then it will be hard. Okay, you see what I mean? So what we actually talk about here, we don't actually deal with the corner really well. But what will happen is that if you don't actually add the corner, if you don't have the data point at the corner, but you actually truncate it closer and closer, you will get a very sharp gradient. But it cannot represent a non-smooth plasticity. Okay, so some material have non-smooth plasticity like a crystal. That means if you actually really using it at this point, they really have a sharp corner that make parsec flow in here and here equally valid. But we can deal with it in the geometric approach. So here we will focus on only generating smooth functions. Okay, simply because we need the term anyway. The last thing I want to talk about is the same thing as the elasticity. In general, I would recommend that you use the RE-LU learn functions, but here is the thing. Usually at this corner, you really have this corner is continuous, but it's C0 continuous, meaning that if you take the derivative, basically it's like the tip that I just showed you. You have to the corner actually doesn't have a derivative that are actually smooth, so it has you can call it a with discontinuity, and that could actually lead to a problem if you actually rely on the derivative term. So you can actually add a multiplier layer to overcome that. Another possible way is to use the hyperbolic tangents, or actually using something called what is the name? Extend RE-LU that actually have a regularization here. So instead of having a jump, the regularized versions of the REU have a little bit of regularizations. Okay, so if you take the gradient here, it still changes really fast, but it's no longer a jump, not a sudden change. So you can do this check, but in general, you would find that you have different difficulty in solving the non-convex optimization problem. Okay, so the more here is actually the rest. Once you actually get the extensions to get the intercore, if the shape is simple, you can apply the particle matching technique that we just talked about, or you can simply another possible approach is that you have the outside data you can simply add a constraint in your learn functions by enforcing the gradient to be unit, to equal to 1. Okay, just after you train it with the data, you just add this constraint there. It would help you extend the data. Okay, you see what I mean? Because if it's just like a physics info neural network, you can just not adding new data point, but simply adding a new constraint. Because the unit has to be equal to 1, the only feasible shape is actually to extend that corner. Okay, but I won't recommend that you only have f equal to 0 and simply expand that. Another possible approach we will not cover is using the narrow band method, which is kind of like level set thing. But instead of populating it everywhere, you just actually propagate a few contours that are actually close to f, because it's all you care. But it doesn't, in practice, doesn't really matter. I'm I hope to try to avoid too much self-promoting, but if you actually want to finish the homework, one guideline is to look at this algorithm in this paper. And then you can just follow this algorithm. It tells you the preparations. You can think about it like a cooking recipe. Okay, you prepare the data, you amend the data, you do the learning, that's it. Okay, then you get the yield functions. After you get the yield functions, you need to implement this code, and because our course is actually not a plasticity course, we actually have implemented the overall skeleton, or when we say we, that means Ming is actually implement the overall skeleton. You just need to plug in the yield functions, and that's it. Okay, so the focus is on learning the yield functions. Now, in this algorithm, you can see that this has one parameter. That is actually the radius of radius parameter of the yield functions. In your case, it's just this one is actually equal to 0, and then it's actually not parameterized as an additional degree of freedom. You simply have a yield function that doesn't move. Okay, just to simplify your problem. In research, I think that except for metal, you won't really have perfect plasticity that much. Okay, so and I get asked from time to time, why don't I just write a if loop? If the stress is greater than this, I just correct the stress. The thing is that it won't work. Also, if you do that, if you actually put a cap on the stress, you can actually probably get this thing okay or whatever. But if you unload, you would actually go through this path, which is actually not physical. And then if you want using it for solid simulations, it would be disaster. Okay, so we'll run through that. Last comment I would like to talk about is that there are also physical constraints. You can fine-tune the yield surface. So the approach that we often use in the machine learning is that I will first try to create the learn functions that fit the data first, and then I'm going to apply the additional constraint to fine-tune the yield surface to change a little bit of the shape to make sure that I actually don't have any bumpy pattern. I can actually correct it. It's similar to making a sculpture, okay? When you make a sculpture, you get roughly the shape, and then you use a different light to actually fine-tune the fine detail. You can think about it like that. So you can have additional training after you get the initial shape to actually correct it. I just point out one particular check that would be interesting and quite intuitive. In general, you want the energy, so the plasticity is actually can only be triggered if you don't store all the elastic energy. Okay, when you compress the material, elastic energy gets stored, and then when you unload the material, using it to go back to the original shape. Okay, so if you store all the energy, there's no plasticity. The plasticity actually requires you losing some information to have the degradations. Okay, so in the 1D plasticity, you have that strain and stress, you go up and go down. Okay, the important thing is that in order to trigger that plastic strain, I have to lose some of the energy. And that energy has to be positive. The interesting thing is that actually related to how the plastic flow directions and then the eigenvalues align with each other. So for example, if you actually have compressive strain, and then you actually, if you compress the material and you create plastic strain that are actually in tensile direction, in opposite directions. Okay, so you may actually create something that actually violate the Pascal dissipation, meaning that you may actually gain energy by having plasticity, which physically make no sense. Okay, so one easy way to doing it is actually to add a little bit of penalty term after you training it and do the retraining. This could be simply done by adding this term there, but then the sign function is actually not smooth. And actually, if you need to, in order to update the neural network, you actually need the automatic differentiations, which actually translate to you need the gradient to be sufficiently smooth. So you can actually using the approximate smooth function, just like what we talk about in the RE/LU, to give you some smoothness so that you won't actually have a exploding gradient when you actually add the physical constraint, okay? You see what I mean? So think about when you add a constraint, make sure that your constraint has some smoothness on it. In principle, you can put everything you think is right on it. In practice, you actually need to understand that you really need to compute a gradient. Anything that requires you to compute a gradient, the gradient has to exist, right? And it should not have two gradients, okay? You understand what I'm saying? You have to have one gradient. It could be very sharp, but it still have to have the that function will have no effect. Okay, it will be just zero because it's a sign function, is property. Okay, so this is actually the check. Okay, and this is actually the enforcement. As you can see, a lot of the loading. This is actually 3 different color to indicating a real polycrystal material actually getting yield, and then it mainly have isotropic yielding, but it actually have some distortions. Okay, it translates to a perfectly symmetric loading to something that are no longer symmetric or symmetric in these directions. You see, initially the symmetric is here, but it's spin a little bit. Okay, so this is something I think is quite interesting, at least for me. But the interesting thing I would like you to see is the following. Because the data is obtained from reality, the reality, of course, will fulfill all the physical constraints. So presumably, if you have a lot of data, you don't actually need the physical constraint. You understand what I'm saying? Because you're obtaining the data that fulfill that constraint. Like if you have an isotropic material, okay, and then you actually collect a lot of data, you can enforce the isotropic behavior just by using a lot of data, okay? But here you can see that if you actually reduce the data, then the physical constraint become more important. Okay, because the physical constraint gives you the necessary control to before the learn functions become deviate from the reality. Of course, then there are some constraints that are not necessarily physical. You need to identify that. So in here, you can see that I basically, in the plasticity chat, I create a chat. Okay, here, if I actually have all the shape that are actually funny, maybe something like this, I'm just going to penalizing it. But if the shape is actually okay, if it doesn't actually create any negative passing flow, the functions. Okay, sorry. I think you need to put the bracket there to make it to be normalizing it. But you get my point. Okay, so this is only for corrections. And if you actually look into the details, you will find out that if you actually just do classical training with the RE/LU, you just trap a small portion of the point, but that small portion of point can make your simulations become not doable. Okay, just a little bit corrections. And you can apply other type of corrections or inequality using that similar trick. So the inequality can be enforced by actually using the sign functions and then with a little bit of smoothness so that you make sure that none of it is violating that. Okay, you may still on the boundary, it won't pushing it, you won't push this point up to here, but it will make sure that nothing go to the negative. It's like a net, right? You understand what I mean? It's like a safety net for the circuits people that fly, okay? If they fall, you go back to zero, okay? So it's like what I did. If I did a perfect job, it would be as if I did nothing. So you see what I mean? I think that's the criteria of being a professor, right? Okay. Anyway, so I think the rest of it is in class tutorial, and I will ask the whole class, if you can, please open the tutorial 2. This time I use a different way to put the tutorial. I just put it in Canvas, and you should be able to open it. If not, I can give you access right now, and then I will just open the repository.